In this lecture, I'm going to talk about motion when you have a constant acceleration. This is particularly important because if we're near the Earth's surface, the acceleration due to gravity is constant. So there's many examples that involve constant acceleration. I'm not going to derive these formulas. You can read through the textbook. They may derive them, and we will probably derive them later in the course. Here's our formulas. The velocity is equal to V0 plus AT. If we think about it, this is almost intuitive. That your velocity, if you started from rest, would just be your acceleration times time if you had a constant acceleration. However, if you don't start from rest, it'll be your initial velocity plus the acceleration times the time. Your position is given by x0 plus v0t plus 1/2 at squared. Let me go ahead and define some terms. V0 is your velocity at t equals 0. We usually call that our initial velocity at time 0. X0 then is just your position at t equals 0. Those are probably the two most commonly used equations. If we do some manipulation with those, we can come up with some others that are also helpful. Really important though, these equations are only applicable for constant acceleration. These are constant acceleration formulas. We've got v squared equal v0 squared plus 2a delta x, and that the average velocity is v plus v0 divided by 2. This second equation was found by solving this first one for t and substituting it in and then doing a little rearranging. But it simply says the square of the final velocity is the initial velocity squared 2 times the acceleration times the displacement. Another way you could have written that, remember displacement, could have been written as x minus x0. But we usually just write it as displacement. This last one, if we think about it, is fairly intuitive. It just says that the average velocity is your beginning velocity plus your final velocity divided by 2. Now that's not true if you don't have a constant acceleration, but it's easy to show it's true if you do. Assume you accelerate from a constant speed of 10 miles an hour up to 110 miles per hour at a constant rate. Okay? Well, if you think about it, what would be your average velocity if you went from 10 to 110? If you did 120 divided by 2 is 60. This just gives you the speed exactly in the middle of your initial speed and your final speed. Okay. These are all really helpful for solving constant acceleration problems. So we're going to look at a couple of problems. One more thing, if you haven't found it yet, I did put a formula chart for Physics 2425 in Blackboard. That would probably be worth your time to print off and keep handy. I may revise it towards the end of the semester, and if so, I'll replace it and let you know. But it's got all the formulas that you're going to need for the first 3 units, I believe. So here's our example. Suppose we have a small plane, talking about an airplane, that can accelerate at 2 meters per second squared. Probably should put, there we go. A small plane can accelerate at 2 meters per second squared. It must reach a speed of 27.8 meters per second to take off. If the runway is 150 meters long, can the plane reach that speed in time? And there's more than one way to solve this problem, but one approach I like to use anytime I solve a problem, if I like to write everything down that I know. All right, what do we know? We know that we can accelerate at 2 meters per second squared. We know that the initial velocity would be 0, and we need that final velocity to be 27.8 meters per second. Okay. We also know that the runway is 150 meters long, but what we don't know is how far that plane is going to travel before it reaches 27.8 meters per second. I like to take a twofold approach. First of all, let's just think about what we can easily find out. I'm going to put down two formulas. Our first is V equal V0 plus AT, and our second one is X equals X0 plus V0T plus 1/2 AT squared. I can usually solve any problem with those two, although sometimes using one of the other formulas might actually save time. But I know if I look at this first one, I know everything that goes in it except t. It would be really easy to see how long it's going to take me to go from a speed of 0 to a speed of 27.8 meters per second. So I'm going to take this formula and I'm going to plug in. V is 27.8. That has to equal the initial velocity, which is 0, plus the acceleration, which is 2, times the time. This is easy. If I divide by 2, I see that goes in 13.9 is going to equal t. It's going to take my plane 13.9 seconds to reach that speed. How far is it going to travel in that 13.9 seconds? Well, I'm going to use the second formula now. The second formula says, well, now I didn't say what x0 is, but in most problems, we can assume that we're starting from 0. I'm going to let where the plane starts be 0, and I'm going to see where it ends up. V0 is also 0. Start with initial. 13.9 seconds plus 1/2. The acceleration was 2. 13.9 seconds squared. I'll need a calculator. All of that is 0. But 14.9 squared is 193 meters. Let's see how many significant digits. Well, we did have 3. That runway is definitely not going to be long enough. It will need to be redesigned. Now, there is another way I could have worked that problem, and it would have actually saved me from having to do a 2-step problem. Although I like the 2-step because I understand it well. The other possibility would be, hey, I had this formula a minute ago. V squared is equal to V0 squared plus 2A delta X. A lot of times I say, look for what you know and see what you can figure out. We want to know this distance right here. What is that displacement going to be? Well, the V squared is going to be 27.8 squared. V0 was 0, and that has to equal 2 times 2 times delta x. So if I do 27.8 squared and divide by 4, I see that the displacement is 193 meters. Like I say, this equation was made by somebody already combining those 2 equations so that you didn't have to stop and solve for the time in the middle. Okay. Let's do another problem. This one's probably a little, we'll have several more problems. We'll decide which ones we're going to do. Let's do at least one more. How long does it take a car to cross a 30-meter wide intersection if it accelerates from rest at 2 meters per second squared? So we have a car parked at an intersection. Light turns green. This car can accelerate at 2 meters per second squared. And how long will it take if that's a constant acceleration to cross the intersection? Let's look at everything we know. We know we started from rest. We know that the acceleration is 2 meters per second squared. If we assume our initial position is 0, then our final position we're interested in is 30 meters. Another way we could put that is we know that our displacement is going to be 30 meters. This problem doesn't mention time because it actually is trying to find time. If we set up our equation like this, whoops, x equals x0 plus v0t plus 1/2 at squared, we're going to need to solve for time. This is 30, this is 0, this is 0, this is 1/2 2t squared. This one came out really nice. It looked like we might have a difficult quadratic to solve, but we really don't. We end up with 30 equals t squared. If I take the square root then, I'm going to get the time it takes is 5.48 seconds. one that's a little more challenging. In this problem, this is an example where we're going to consider a speeder passing a police officer. Okay, we have a speeder that happens to be traveling at a constant 150 kilometers per hour. And we have a police officer who begins from rest and accelerates with a constant acceleration of 5.6 meters per second squared. The assumption is the car and the police officer at the same point at time t equals 0. So you can picture a situation where here's x equals 0, and this is t equals 0, and we have a car going a constant 150 kilometers per hour, and I think this was supposed to be maybe a motorcycle officer. He is parked, but he's going to accelerate beginning from rest at a constant 5.6 meters per second squared. Our question is, how long will it take for the police officer to catch the speeder, assuming that the speeder does not speed up or slow down? That's kind of unrealistic. People tend to either, when a police officer comes after them, want to speed up to see if they can get away or go ahead and slow down and pull over. We're going to assume he keeps going at a constant speed and doesn't realize he's being chased by the police officer till the police officer actually catches up with him. Okay. One of the things we see right away is we've got a mixture of units. We've got acceleration in meters and seconds. We've got the speed of the car, the speeder, there's the police. The speeder's in 150 kilometers per hour. So we'll want to change that to meters per second. That is 150,000 meters, that's a kilometer, over 3,600 seconds. And we see that our speed there can be changed to 41.667 meters per second. Notice I kept 5 digits, way more than we need. The number of significant digits in this problem is going to be 2 at the end, because that's 2 and that's 2. But if I round this to 42 right here, I'm going to create an unnecessary amount of error. So I'm not going to round till the end. So I know that this is the constant speed here. This is 41.667. All right. I'm going to need room, so I'm going to erase some of this. Think about what we know. We know for the police officer, his initial velocity is 0, his acceleration is 5.6, his initial position is also 0. For the speeder, his initial velocity is 41.667. His acceleration is 0. He is not accelerating. He's at a constant speed. And his initial position is also 0. What does it mean for the police officer to catch the speeder? It means that they're at the same location. All right, let's look at that. So we need the location of the police officer and the location of the speeder to be the same. We can find both of them by using that long formula. Position, here's our formula, x equals x0 plus v0t plus 1/2 at squared. For both of them, this is 0, so we can even take that off. There won't be an x0. So for the police officer, his initial speed is 0. So 0 times t plus 1/2, 5.6, left off the square, t squared has to equal. Now we come over here and we do it for the speeder. His initial velocity is 41.667 times t. His acceleration is 0, so I don't even need this 1/2 at squared because that's 0. So this formula, in fact, I can leave that off. You can see right here. This formula tells me how far the police officer travels, 1/2 5.6 t squared. And this formula, 41.667 times t, tells me how far the speeder. I just have to solve that. There's a couple of ways to solve it, but one of the things that we notice, let's just put it all on one side. That's going to be 2.8 t squared minus 41.667 t has to equal 0. One way we can solve a quadratic equation like this is simply to factor it. They both have a common factor of t. So we have t times 2.8 t minus 41.667 has to equal 0. We're going to get two solutions. One of the solutions is t equals 0. Well, that makes perfect sense because we said at time 0, both the police officer and the speeder have a position of 0. They were at the same spot momentarily, but of course the speeder was traveling much faster. If we solve the second part, this second factor, I have to say 2.8 t has to equal 41.667. So t will equal to two significant digits, 15 seconds. So it took 15 seconds for the police officer to catch up. We can go back, we can even see how far they traveled. How far would they travel in 15 seconds? Let's see. If you're traveling at a constant speed, the speeder would travel 41.667 times 15. I'll type that in and just double check. 41.667 times 15. It's going to travel 625 meters. The police officer, his position worked out to be 1/2 5.6 times 15 squared. I want to do one more thing. I should point out when I solved for t, I rounded it. The exact value of t that I got was 14.88 seconds. And I really want to use that here so we get better results. So 14.88 seconds times 41.667. It come out to be about a little less than 625, so about 620 meters. If I do 0.5 times 5.6 times 14.88 squared, whoops. That also came out to be 620 meters. Of course, that's exactly what I expected. That means he caught up. Now, the only problem with this is it's probably not very realistic. So in order to catch up with the speeder, he has to go much faster. How fast would that police officer end up going? We know this is again for the police officer. V equal V0 plus AT. He started off at 0. He's accelerating at 5.6. If he does that for that 14.88 seconds or 15 seconds, what we see is he'll end up going about 83 meters per second, which, in case you're wondering, is about 190 miles an hour. So not very realistic to think. Notice he has to go basically twice as fast as the speeder by the end, so that they had the same average speed. All right, let's move on to this next section, and the last section for Chapter 2. Free fall. When we talk about something that's in free fall, we basically are saying that the only force acting on the object is gravity. So we have to really ignore air resistance, which is not always appropriate. It's perfectly appropriate to ignore air resistance if we're talking about dropping cannonballs. It's obviously not appropriate to ignore air resistance if we're talking about things like falling feathers or leaves or parachutes. It was Galileo who figured out that as long as you're near the Earth's surface, all objects fall with the same acceleration. We have constant acceleration due to gravity, and that constant acceleration due to gravity is normally called g, a lowercase g, and it's 9.80 meters per second squared. That's called the acceleration due to gravity. Later when we talk about gravity, we'll learn that if we move far enough away from the Earth's surface, we can't treat it as a constant acceleration anymore, because the force does in fact depend on how close we are. But as long as we're reasonably near the Earth's surface, that's acceleration due to gravity. Okay? Most of the time, we need to remember that this is going to be directed downward. So when we put this acceleration into many of our problems, we may want to put it in as negative. It really depends on how we set up our frame of reference. If we take the same formulas that we had earlier when we were talking about constant acceleration, this is constant acceleration. So we still have v equals v0 plus at. But now instead of x, we usually use y. So y equals y0 plus v0 plus v0t plus 1/2 at squared. So now we are assuming we're only doing linear motion. So our velocity, any initial velocity, is vertical, up or down, and of course our acceleration is vertical. V squared would equal v0 squared plus 2a delta y, because it's a vertical displacement, and the average velocity is still v0 plus v divided by 2. So nothing changed except where we used to have an x, I now put a y to show we're working a problem that's vertical. Most of the time, we're going to set up our frame of reference where up is positive and down is negative. If we do that, our acceleration is going to be a negative 9.80. We don't always do that though. In fact, our first example, we're not going to do that. A ball is dropped. Okay. You need to learn right now when something's dropped, that means that the initial velocity was 0. If I'm holding this marker, it has a velocity of 0 when I drop it, and it will accelerate down. Okay? So just when they say something's dropped, that's different than throwing it down forcefully or throwing it up forcefully. If we just drop it, it starts with an initial velocity of 0. From a tower, $70 meters high. But we're going to assume that the ball itself is 70 meters above the ground. How far will it fall? Let's change my words. How far has it fallen? After t equals 1, 2, and 3 seconds. This type of thinking really let's get a picture. Always a good idea. So here's our 70-meter high tower. Here's our ball. In this case, we're going to go ahead and just since everything's happening down, we'll just let down be positive. We'll start up here and say this is y0 equals 0. Okay? How are we going to find its position? Well, we know, so I'm going to take down as positive. That's the exception. Most of the time, I'm not going to do that. Most of the time, I'm going to say, hey, we started at 70 meters and we hit the ground, we'll be at 0 meters. But for this example, we're going to do it the other way. So down is going to be positive. I know that y is equal to y0 plus v0t plus 1/2 at squared. But my initial position is going to be 0. And my initial velocity is going to be 0. So those are both going to go away. So how far something falls when you drop it is just given by 1/2. The acceleration is 9.80 t squared. What is 1/2 of 9.8? So really we've got it even simpler. 4.90 t squared. If I make a table, kind of helpful sometimes. This is t, this is y. At t equals 0, of course, if I plug in 0, it's at 0. But at 1 second, if I plug in 1 second squared, it's going to be at 4.9 meters. If I plug in 2 seconds and do 2 squared, this is almost 5. 2 squared would be 4 times 5. It's going to be close to 20. And it actually comes out to be exactly 19.6 meters. If I wait for 3 seconds, that's going to be about 9 times 5. So I think it's going to be very close to 45. It comes out to be 44.1 meters. So we found it 3 times. It's t equal 1, it's fallen 4.9 meters. T equal 2, it's fallen 19.6. 3, it's 44.1. Notice it's accelerating at a constant rate. It is not covering a constant distance each second. Each second it's traveling faster than the second before. So each second it's covering more and more distance. It only went about 5 meters during the first second. It went about 15 meters during the second. The third second, it went about 25 meters. So it's definitely going faster. So if we graph it, which is kind of an interesting thing to look at, what we see is 10, 20, 30, 40, gotta go a little past 40, 1, 2, 3. It started here at 0, 0. At 1 second, it had gone approximately 5. At 2 seconds, it had gone approximately 20. And by 3 seconds, it had gone approximately 45. Notice it forms a parabola, which is exactly what we expect, because remember, we said we found its position because it was equal to 1/2 AT squared, or 4.9T squared. So it was, in fact, a quadratic function. The distance that it falls depends not on the time, but on the square of the time. So we're not surprised it's quadratic. Another question that they ask related to the same idea is, when will it hit the ground? Or in this case, when will it fall 70 meters? If we use our formula that we started with, we want to know when y will be 70. That was 0, that was 0, 1/2, 9.8, T squared. Watch out, I accidentally left the 2 off. It's really easy. That depends on T squared. So 70 has to equal 4.9 T squared. I'm going to have to divide by 4.9 and then take my square root. So 70 divided by 4.9, I end up getting 14.2857 equals T squared. And then if I take a square root of that, I get that the time is 3 significant digits? 3.7, comes out much bigger. There we go, 3.78 seconds. I had to round to get that correct. So if we had figured out how far something could fall in 4 seconds, if I put in 4 here, what we'll see is that's over 70. And of course, it can't really fall over 70. Yes, it would have fallen 78.4. So 4 seconds would have been too long. So this is a really reasonable answer for our problem. Now, let's do one more consideration. Let's go back up on the tower, but let's not drop it. Remember, when we dropped it, it took a little less than 4 seconds to hit the ground. But what if instead of we dropping it, we actually throw it down? Suppose it's thrown down from 70 meters. At 3 meters per second. That's going to change our equation. We have y equals y0 v0t plus 1/2 at squared. If we continue to treat down as positive, then this will be a positive velocity. So we want to find out when it's going to hit 70. This was 0. This was 3. So this time we have a little more challenging algebra. There's lots of ways you can solve a quadratic. One of my favorite ways to solve a quadratic is to use a graphing calculator. I'm trying to see if I see a graphing calculator close at hand. I have this little one. Okay, I found this one. It's not my favorite. My favorite is my color calculator, but unfortunately, my color calculator is dead right this minute. The best way I know to solve this in a calculator is to go ahead and let it equal 0. If I rearrange this equation, I get 0 is equal to, and I'm going to just write it like this. I have to move this 70 to the other side. If I type this in y equals on my graphing calculator, and I hope you're all really comfortable with that, y equals 4.9. Of course, you have to use x instead of t, x squared plus 3x minus 70. I want to know when that equals 0. So this is what the calculator says. And in y2, I'm just going to put 0 because I want to know when this equals this. So y2, I put in 0. And now I just want to see where those two lines cross. If I graph it, I might have to play around with the window a little bit. Probably can't see, I'm zooming out. Unfortunately, I don't think there's any way. Perhaps I can get this close enough. Oh, there you go. I zoomed in and you can see I have a graph of a quadratic function. There's two places where that graph crosses the x-axis or where that graph is equal to 0. Obviously, the time cannot be a negative number. So even though this has two solutions, a negative and a positive solution, I know that the only correct solution is the positive one. So I'm going to go second calc, and I'm going to choose intersection, and I'm just going to see where does that graph intersect the x-axis. And when I do, it tells me the intersection is x equals 3.49 seconds. That's a little bit faster than before. Remember before, and this is really t now. That's our time. Before, when I didn't throw it down, it took 3.78 seconds to reach the ground. But by throwing it, it reached the ground a little bit faster. If you guys have trouble with calculus, if you have trouble with algebra, you really need to work on it because we're going to use algebra a lot. If you have trouble with a graphing calculator because you haven't used one before, let me know and I'll see what I can do to help you with that. Let's do a totally different problem. Again, this is going to be a free fall problem. This time a ball is thrown upward at 15 meters per second. From a height of 50.0 meters. I left out the part where the boy is standing on a cliff, but I'm going to draw it in the picture. So we have a ball thrown upward at 15 meters per second from a height of 50 meters above the ground below. a lot of things that we can answer. So let's just draw a picture. Here's a cliff. Here's somebody standing on a cliff over here. And he's going to throw a ball so that it starts at a height of 50 meters, goes up, because he threw it straight up, and then reaches some maximum height and turns back around and falls all the way back to the ground. So the ball starts out 50 meters above the ground. It's thrown upward at 15 meters per second. There's quite a few things we can answer. We can find the maximum height and the time in the air. Those are both good questions. We could find the total distance the ball travels. First, let's talk about maximum height. The acceleration due to gravity is approximately, not exactly, 10 meters per second squared. We use 9.80 in the problems, but let's just talk about it as 10 for a minute. If I have something in my hand and I throw it upward at 30 meters per second, let's think what happens each second. I throw it up at 30 meters per second. 1 second later, it's going to be going 20 meters per second because the acceleration due to gravity is a negative 10 meters per second. So I throw it up at 30. A second later, it's going 20. Another second later, it's only going 10. After 3 seconds, it's going to have a velocity of 0. If we use that rounded 10 instead of 9.8. So I throw it up at 30, it's going to take it 3 seconds to reach a velocity of 0. 1 second after that, it's going to be going negative 10. And 1 second after that, it's going to be going negative 20. And 1 second after that, it's going to be going negative 30. That acceleration doesn't change. It's a constant negative 10. The interesting place is when you reach the top, v is equal to 0 at the top of the path, because that's the place where the velocity goes from being positive to being negative. Well, the only way you can go from a positive velocity to a negative velocity is to go through a point where the velocity is equal to 0. So if I want to find the maximum height, I probably want to figure out when does it stop. Okay, let's write down our knowns. We know V0 is 15 meters per second. We know Y0 is 50 meters per second. And we know acceleration is negative 9.80 meters per second squared. There's our given information. At the maximum height, V is 0. So if I use this formula, V equals V0 plus AT, I want to know if this is 0, and this was 15, and this is negative 9.80. What's T? How long to reach the maximum height? Well, that's going to be 15 divided by 9.80. Comes out to be 1.53 seconds. Now, that's the time it takes to reach the maximum height. That doesn't actually tell me what the maximum height is. If I want to know the maximum height, I have to do y equals y0 plus v0t plus 1/2 at squared. But I know the time, and this is really close. It comes out to be, if I wanted to put in more digits, I really don't need to because it's like 1.5306, but we can do that. So this was 50, this was 15, this is 1.5306 plus, the acceleration is negative 9 points, so this is minus 4.9, 1/2 and then 1.5306 squared. If I want to plug all that in. And that'll tell me how high above the ground it is. So I have 50 plus 15 1.5306. I just put these extra digits so I don't get a rounding error too soon. Minus 4.9 and then 1.5306 squared. I get 61.5 meters. I rounded it. Well, what that tells me is it started at 50 meters, is that it goes up about 11.5 meters before it turns around and hits the ground. That's one question that I can answer. How high was its maximum height? How long did it take? Now we can look at the problem and tell it only took 1.53 seconds to reach the top, but it's going to take a lot longer to come down. Let's see if we can find how long it's actually in the air. Now, to find the time in the air, we use this formula. Now let's think. When it hits the ground, y will equal 0. This is y equals 0. This was y equal 50 where we started. So we have 0 equals 50 plus 15t. 1/2 of 9.80, this is negative 9.80, minus 4.9t squared. This is another one of those quadratics that probably the way that I want to solve it is to actually graph it in my calculator. I can put it in right where I had that other one. 50 plus 15 times x minus 4.9 x squared. I use x's instead of t's. And I just want to find out when that's going to equal 0 and graph it. Again, I see two answers. I see a negative and a positive. I know the positive is what I want. Second calc, I'm going to do an intersection. I'm looking for the intersection between y equals 0 and y equals all of this. And I get that t equals 5.07 seconds. There are other questions that they could possibly ask you. How far did the ball travel? Well, we know that it was 61.5 meters here. So this was another 11.5. So the total distance it traveled would have been 11.5 seconds on 11.5 meters on the way up and 61.5 meters on the way down. That's going to be 73 meters. But I'm still using every one of these problems, these constant acceleration formulas. It's a matter of realizing, what do I know? What are all my known values? What am I looking for? And then deciding which formula is going to help you find it. I'm hoping that we'll get together and have some collaborate or Google meetings, and perhaps we'll work more examples at that time. That's it for Chapter 2.